From Microbe TV, this is TWiEVO, This Week in Evolution, episode 64, recorded on January 20, 2021. I'm Vincent Racaniello, and you're listening to the podcast on the biology behind what makes us tick. Joining me today from Salt Lake City, Nels LD.
Hey there, Vincent. Good to be with you from LD Lab Studios. It feels like kind of a optimistic day unfolding as we're recording here on January 20th, a big day in our nation's history.
Yeah, I do feel some optimism. Yeah, we'll see what happens as the days move on. But yeah, it's I have to say it's a day I've been waiting for 4 years.
I hear you. And maybe, the optimism, good reasons for reserving that, but maybe some relief, at least. That's my maybe overriding emotion at the moment.
Yep.
Just as things are transitioning and looking to go smoothly. Quick update here. So instead of the weather, we've been comparing SARS-2 and vaccination number notes. That's starting to move in a slightly more promising direction. So I just checked in the last couple of days, the number of cases is down a bit. The number of positive tests is down a bit in terms of the percentages, both still too high, but at least the trend line's looking encouraging. And then the reverse happening, more vaccinations happening. And in fact, if you do a infection to vaccine race, the vaccines are now winning roughly by 3-1, at least in the last couple of days. And that's an improvement.
This is in your state, right?
This is in the state of Utah. Still, a lot of the question marks and anxiety over some anxiousness over what's the supply of vaccines going to look like here, in the short term, in the coming month or two. But moving into some of the next phases. So certainly here at the hospital, the University of Utah Academic Medical Center, most of the frontline folks are now vaccinated, some of which, an increasing number, already second vaccines on the Pfizer in particular. And then the Moderna, both of the mRNA-based vaccines are both being distributed widely across the state with the hiccups that we've all been hearing about as well. How about there in New York? It sounds like is that a similar story for how the vaccine is deploying?
We had some issues in New York and distribution and it's a problem still. I did get some numbers. New York vaccine distribution. Let's see if we can get some numbers here. COVID-19 vaccine. Blah, blah, blah. Phases, tracker here. Tracker. Updated 11 a.m. So New York State has received 1.19 million doses and has administered 900,000. So they have administered 77% of the doses that they have received. New York City, of course, receives the most, 500,000, and they've administered 75%. So it's not great. You should be given more than that.
Yeah,
give them all out.
I think I completely agree. It's definitely a massive logistical situation, but kind of stumbling out of the blocks. And that's the question now: is do we start getting some stride and some momentum here? And then obviously this is all entangled as well with the political transition in our country that we were talking about, and so this will be, I think, on the top of our minds in the weeks ahead. I did a quick comparison. The data is already probably slightly out of date, but something like for first vaccinations, New York is roughly with that 1 million level. That would apply to about 5% of the population of the state, whereas in Utah, our numbers are a lot lower, but the percent is about 7%. So similarly, very different states, very different numbers, but roughly the same in terms of fairly modest population coverage at this point. So really hoping that ramps up, and that'll be part of the theme, I think, of our podcast today as we revisit the evolution both of the virus, but also some new late breaking info on the evolution of the immune responses to it, and I think some kind of good news, bad news situations that we'll tackle today.
The administration plans to immunize 100 million people in the U.S. in the next 100 days. So that's a good plan. I think bringing federal involvement in is good, and it can't hurt. So let's see what happens. I have to say I got my first shot last night here in New Jersey.
News.
New Jersey last week opened it up to anybody 65 and up, and I make that by 3 years, Nels.
I'll drink to that, Vincent.
One of the good things about being older.
That's right.
And so I got it, and it's Moderna, and my arm is just pretty sore. It's more sore than a flu shot, I would say. When you go, you sign up on an app, and then immediately they make you an appointment for your booster. So I have an appointment for February 16th to go right back. And it was at a local college, and I was very impressed. They had a very good organization, right? They keep everybody distant. They have traffic control, very proper pedestrian control, a lot of signage. And, people are doing a good job. I'm very happy about that. So
that's really great news, and pretty exciting to think about as we're podcasting how some of the cells in your arm, in particular, the muscle cells are cranking out.
I was just thinking that. I was thinking
cool?
that. I was lying in bed last night and go, oh, my cells are making spike, man. My cells are making spike. This is a protein I've never seen before. Holy crap. Who would have known? Less than a year after we started talking about SARS-CoV-2, I got spike in my arm. That's amazing. That's amazing.
It really is. That's like, I think for me, hands down, that beats getting a tattoo on your arm. Having your cells producing a virus protein, that's kind of a metal, has some good, kind of good energy to it.
Yep.
And what we're hearing, we'll talk about this in some detail, is some good early returns on what our what immune responses are looking like, especially after that second dose that you have scheduled. So I'm still waiting. And that makes sense given the rollout and, my not quite as advanced age.
You're 40 years old, right, man?
I am. Not too far behind, actually. But currently in Utah, the number is 70 years old for getting appointments. And they're all booked now, I heard yesterday on the radio, until February. And then, with also some crazy sort of intermingling of politics. In both good and bad ways, but teachers getting a higher priority, especially kind of in that K through 12 window. So in Salt Lake County, where Salt Lake is located, this is the only county that has not done in-person schooling yet, to their credit. And then a somewhat awkward negotiation with the state legislature in particular to get them back in session, but on the condition that the teachers get some priority in terms of the vaccine. And so that is kind of unfolding in real time. And so I'm kind of sitting back, trying to hunker down. I think this is the time to play it the most safe, right? Especially as we're either going through the vaccination process, which takes weeks to get that booster and then that immune response. What a perfect time to not get infected and let this let our immune responses ramp up for this. Yeah. So I'm glad to hear that, Vincent. That's great news. Okay, so speaking of that, let's jump right in. I think again, a little bit of a tasting menu here. We're not going to do our usual TWiEVO deeper dive into a lot of the details. We have a lot to cover, and in fact, we kind of, I think, set the table for this in our last episode. Feels like it was 3 weeks ago, Vincent. It feels like 3 years ago when this new variant sort of got all of its attention, the B117. We'll talk about how that story has progressed, how we know a few new things, but I think there's still a lot of questions out there. But then I think what I wanted to do and bring to today's episode was we've talked a lot for good reasons about what's going on with virus evolution, what's going on with the diversification of SARS-2, but we've talked less about our own kind of, immune response and what does that look like going forward. And in fact, there's more than two, but two in particular studies that kind of caught my attention that speak to this in some, I think, good detail with some good studies. So the first one is the title of the paper that was just published in the journal Nature is Evolution of antibody immunity to SARS-CoV-2. This is a massive collaborative group, mostly New York based. So some of your colleagues in your neighborhood there, 11 first authors on this paper. That might be that might be a new record. How do you? But really a response, I would say, to kind of emergency science situation here, right? Where this crew came together, I think back in March, and started trying to tackle this, sort of put the pieces together to do this multidisciplinary attack on how our immune system might respond to natural infections, of this case of SARS-2. So led by Michael Nussenzweig, who's at the Rockefeller, other colleagues there, Paul Binoche, Theodora Hatziananu, say her last name 5 times fast. Other folks at, and sorry, Theodora, I'm sure I didn't quite get that right. Other folks from Mount Sinai, so Saurabh Mahandru, and then some West Coasters. So from Caltech, Pamela Bjorkman and Christopher Barnes from her lab, coming in with some great, almost like real-time cryo-EM structural information about the interaction between neutralizing antibodies to SARS-2 that our bodies are making to the spike in the receptor binding domain in particular. And so the study is longitudinal. It's looking at folks who are naturally infected with SARS-2 and then judging their immune system's responses at 2 months and 6 months after infections. And so this is probably actually, would be a better topic for your sister podcast, Immune, to have some real immunologists who could decode some of the complications of the immune system. But at least we'll do sort of a light version of it. And so the game here is antibodies, neutralizing antibodies. And these come in different flavors. So the alphabet soup here is the IG, or immunoglobulins of different natures. So IgG, IgM, and IgA. And so if I'm remembering right, I think IgG, you're probably more up to date with your immune podcasting activity, but in IgM, so these are sort of these are the antibodies you're making right now in your arm.
So I'm making IgM, right?
IgM, yep, exactly.
Which will predominate early on because it's a low affinity, but there are 5 IgM molecules joined together by their Fc, so that you can get higher avidity early on before you've done all the somatic mutation and selection, and affinity maturation, and all that stuff. And that's happening now in my germinal centers. So I got a shot in the arm. So my armpit lymph nodes are doing this. They're checking out the protein. And then over the next few weeks, they're going to start making IgG, and then the IgM will go down.
That's right. And then the IgG, and according to this study, kind of at that 6-month zone, the IgG will also follow and start on a decline. But what's encouraging here is the IgA that holds on. It comes down a little bit for kind of on average in the sampling that they did. But this bodes well. So in the IgA, this is getting closer to the respiratory tract, the mucosa, where the virus lives and replicates. So to speak, lives, but replicates for sure, and could potentially get passed on. And so that, and there are other studies from a number of groups who are starting to see similar things. What's kind of unique about this study, including sort of bringing together all of these folks with different skills, the immunologists, virologists, structural biologists, is then characterizing a little more deeply what's going on with the B cells, so the cells that make those antibodies. And what they're observing here and putting out as sort of the main conclusion of their study is that while there's turnover of the B cells, that the B cells that you see at about 6 months after the natural infection, so you said it a moment ago, this idea of somatic hypermutation. So then this is a massively fast diversification process of our antibodies. Kind of, how do you play in this so-called arms race where it's an unfair race, right? The viruses have all these advantages to our own evolution as hosts. So massive populations, short generation times, and loads of mutations, whether this is point mutations, and we'll be talking more about that as usual, or recombination as well, as we've discussed for some of the larger viruses like coronaviruses. And so you can't win. If we were going to play this on a straight up generation to generation, mutation to mutation, we're not even close. But our adaptive immune system has this great property of somatic hypermutation. Also, underlying this is this process of VDJ recombination. These enzymes, RAG1 and RAG2. What I love about this from an evolutionary standpoint is we think those enzymes were co-opted or repurposed from retrotransposons, transposable elements that were ancient invaders of our genome. They've now sort of decided not to just be stowaways in our genome, but have sort of gifted us, genetically speaking, this great activity where our B cells can undergo this process of recombination, somatic hypermutation, and spit out these diverse antibodies. There's this selection process that's happening on this. And so this is specifically what this group looked at, is that process, and actually noting that some of the memory B cells are spitting out antibodies that do have, just by judging how many mutations you see in the collection of those populations of cells, and by looking at the antibody sequences, you can see this process of hypermutation unfolding. And so this suggests that, that these, and they show some evidence through binding assays that these sort of late breaking antibodies have more potency and some ability to recognize the mutations that are starting to accumulate in the spike protein of SARS-2. And so, a little bit of a feeling of the immune system strikes back, that we're not sort of helpless in terms of, we have to see who's vulnerable or who's has some genetic resistance or something, who goes on to have kids waiting for the next generations, but that our immune system in real time has the ability, as they're saying in the title, a little bit provocatively, to evolve to evolution of antibody immunity to SARS-2.
Not the way we think of evolution on this show right now.
Well, right. So I have to do my sort of, aging academic professor, like, let's hold on a minute. How do we define evolution? And so by one definition of, diversification or changes over time, it fits that. What's missing, though, is that heredity, right? So that word somatic hypermutation, meaning that this is happening in our B cells that are not part of our germ. They're not part of our germline. And so that memory kind of ends with us. And so in that sense, we aren't, in ways that we can clearly see, we aren't sort of passing that potentially potent antibody to our offspring. However, indirectly, this system of hypersomatic mutation has evolved. And so in that sense, we do sort of, as the old saying goes, stand on the shoulders of giants, our ancestors, who through a process of natural selection ended up with these great memory B cells that they've sort of gifted to us, that then have this ability to adapt. And so that's actually one of the interesting questions in evolution, is this idea of sort of almost indirect outcomes, and how, because natural selection can't directly act on that. We don't pass that specific variant of a antibody. Since it's this process in somatic cells, we don't pass that from generation to generation. But the system itself, and how does natural selection act on that? Actually, an open question, and I think an important one.
I think it's useful, though, Nels, to look at the title and say, this is somatic, and typically we don't think about that in evolutionary terms, because organisms evolve as they pass on changes in their genome, right? So it's even though it may be considered by some pedantic, it's actually a good teaching moment, really.
I agree, and in that sense, right? I mean, there is selection here on that pool of B cells, the memory B cells, to keep around the ones that are doing some work. There are limits to that, right? And so come back in another 6 months, and are we at the sort of what does the B cell population look like for these folks who are naturally infected, and how much flexibility is there sort of in chasing after the virus? And I think we would predict probably that at some point the virus actually will, in this sort of short-term interface, outcompete the ability of the memory B cells to sort of keep up, in a sense. But that's also an open question. I think I would draw from our experience with other coronaviruses, right? So and in particular, the ones that cause the common cold. And the fact that we still get the common cold all of the time. Very different medical outcomes, obviously, from SARS-2 currently in terms of the nuisance of these colds, but maybe a similar theme of how coronaviruses sort of continue to escape some of the natural immune responses that we mount. But yeah, so anyway, so I think some good news there, maybe hopefully a little bit of balance to the conversation as we're grappling with all of these quote unquote variants of SARS-2, including ones that we started to talk about, B117, that lineage in particular. So before we kind of go there for that update, there's another just late breaking, so similar group, the Nussensvig lab, again, Benash and Bjorkman and others here, not totally overlapping, but just dropped onto the bioarchive a largely overlapping paper that doesn't look at the natural immune responses from infection, but actually found a sample of 20 individuals who received the mRNA vaccine. So just are a little bit farther down the path than you are from your fresh vaccine. So this group, and because, there are a lot of people that are involved in clinical trials, a pretty large population of people who are now weeks on or months on from their second injection. And I think this was both the Pfizer and the Moderna, the vaccine that you got yesterday. And so looking 2 months after the second injection, again, sort of similar immune system or immunological analysis. And I should say, so a lot of the assays here to sort of determine the potency of the neutralizing antibodies produced by the B cells. This is, it's sort of taken out of the context of the natural infection, taken out of the germinal centers, and actually expressing or producing individual antibodies. A tremendous amount of effort for how fast this group has been able to team up and how fast they've been able to sort of turn around some of this. And they're doing binding assays. How well or how much of that neutralizing enzyme antibody do you need in order to bind the spike in the receptor binding domain of the spike, in particular, the main set of antigens that the immune system is seeing. And so doing these assays, they actually, so in addition to, so first of all, the good news, again, as we've been hearing this massively strong, not just this study, but other studies, massively strong immune response, and noting especially after that second booster, that you get immune responses that rival or even outpace what's happening in a natural infection. And again, this, I think, massive success story in, as you were saying, less than a year from going from the virus sequence to these fully deployed mRNA-based vaccinations. Sort of a side note, I think some really good evidence emerging from Israel, where they have so far a pretty impressive vaccination program going relative to the states that we live in, where I think I don't know if you've seen recent numbers, but they're north of 20 or 30% of the population.
I've heard, yes.
Yeah. And doing some, real-time studies of this too, and very much seeing the efficacy in these antibody responses as well, up to the, throwing around numbers like 98%, which for vaccines is just, kind of a slam dunk of responses so far. So far, so good there. But what's really, I think, and this will kind of transition us into back to the conversation about virus evolution, SARS-2 evolution, is they did some assays on some mutations of note that are involved, for example, in the B117, the variant that emerged from the UK. And so those three mutations in the spike protein are 417, 484, and 501. And in fact, 501, some of this variant has been named in some cases after that. That turns out the naming of these coronavirus variants has turned into just a morass, kind of a soup of issues. We'll revisit that. But so very quickly, in the matter of a few weeks, matching together these antibodies that are specifically these polyclonal antibodies, so a collection of antibodies that are being raised as a result of the vaccines against spikes. How well do they bind to the spikes with this set of three mutations, which has sort of been proposed as an adaptive step in virus evolution here. And in fact, they have some evidence that those mutations are probably antibody escape mutations, that there is this, so that this isn't just, as we've discussed at length, the virus undergoing all of this collection of random changes, but very likely that these three have been selected on, and in fact, perhaps this combination of three have been selected on for their property to avoid some of the antibody recognition that you get from your immune response to the vaccine.
So Ed, now as you think these changes, a couple of spike changes, they arise just randomly, right, during viral replication, and then you think they're selected by antibody responses in people? Is that the scenario?
So that's what this work is proposing, and it's not, so it's not like a open and closed case from a virological perspective. So the data itself is quite strong. It's well done. It's a robust measurement in statistically supported difference in antibody recognition, and I want to kind of go into a little more detail on that. But it does, so it raises, and I think we'll talk more, I hope we talk a bunch more about this in the next few minutes, which is, how do you distinguish, why these mutations or how these mutations might be selected, why they're around, and what is the impact for the virology that goes forward, whether that's transmission, whether that's antibody escape, or whether these are sort of overlapping things. And so I think that, there's been a lot of hot air in the last few weeks as well about how we think about what the virus populations might be doing from random processes with founder effects, which we very much know happen and can dominate in early sort of diversification of viruses, relative to evidence, and in this case, I think the best evidence so far, with some other studies very much on the heels of this, or kind of doing this in slightly complementary ways, that there's clear differences in the ability of the antibodies to recognize those mutated forms of the spike. And so this isn't, and I think it's important here to just kind of weigh this. So that can sound like a very scary thing, that you've escaped the antibody response that you've just mounted. But this isn't a full escape. And this is taking individual antibodies from a polyclonal pool, a pool of many, where some are still potent and some are still effective. And so it feels like, and I think a fair conclusion to weigh is that there is some selection happening. And this would, and that we're seeing the first signs of that there's been enough natural infection over the last year that the virus is starting to, that we are seeing the first signs of an evolutionary process here in coronavirus biology.
Well, Nels, why didn't we see it last year? Is it just that so many more people are now being infected?
Exactly right. And so I think that's the best idea here is, in fact, let's put it in these terms. So think about what's happened in the U.S. Just in the last few months. So from the beginning of the pandemic up until I think about November, 300,000 Americans died. And that's, it's just one measure. There's many number of infections, et cetera, that kind of mirrors this. Just in the last month or two, or in the last month, I believe, 100,000 more people have died. Yeah, and so what that reflects is a very different part of it. So it's, time isn't for the virus populations as they diversify. Time isn't unfolding in sort of a linear way. Just as the infections spike, the number of mutations that the virus is sampling also does so. And the real piece of evidence here from an evolutionary standpoint that's kind of starting to put me over the top in terms of thinking that we are starting to see signals of virus adaptation is the notion of convergent evolution. Do you see the same mutations showing up again and again in the same place? And the
independently,
answer,
right? Independently.
Exactly right. And the answer so far is yes. 501, for example, which can be traced independently to variants that emerged from the UK, from South Africa, from Brazil, and more so. And then, and in fact, in this work, the authors note that when they put, so they take pseudotyped viruses, I believe pseudotyped HIV with the SARS-2 spike, and then replicate that virus in the presence of some of these antibodies that lose some of their potency, they, in their experiments, see those same 3 mutations actually arise in the laboratory, right? And so it's building this circumstantial case where and even if 3 weeks ago, I think the circumstantial evidence was a lot more thin than now 3 weeks on, as we're seeing both on the virus side, the independent evolution, the convergent evolution of a lot of the same mutations, still a very messy area, and we'll dig into that kind of on the second half of the show. But then also this I think complementary, on the host side, and how the immune system, what do the antibodies look like, and how effective are they in the face of these variants that are independently emerging? And the fact that you see this, substantial level of escape for some of the monoclonals that are part of our natural response it's starting to build that case. It's starting to add up, for sure. That doesn't mean so, but at the same time, I think what this says more, I think, is that things that we might do as interventions, some are going to be more dangerous than others, actually, when we think about the evolution of the virus. And so if you just do monoclonal antibody treatment, which is happening, right? This is part of those are you will get viruses that will sort of start to go through the hoops very quickly. Yeah. The good news, though, right, is that because of the double barrel of the effectiveness of the vaccine, and also the polyclonal response of our immune system, with that somatic hypermutation sort of coming in at the end, giving us a little maybe extra twist or extra boost of our natural immune responses. I think that first round of vaccines that we're at the beginning of, hopefully very quickly executing on, good reason to be optimistic that this is going to bend the curve, at least temporarily. And so that kind of opens up that question, right? The virus isn't going to fall asleep on us, or take a break from the selective pressures it's facing. And so I think, my prediction, kind of gazing at the tea leaves, is things, if we can actually deploy this vaccine, things are going to get better fast, with some just sort of hints of evidence coming out of Israel, but not out of the woods. And in fact, I think a major turning point for this whole thing is what we do in terms of the boring old public health responses. Are we still wearing masks? Are we still social distancing? Are we, hunkering down? And that's going to have a lot to say about what happens in the next chapter of the pandemic.
Let me make a couple of points here. First of all, monoclonal treatment is pretty minimal in this outbreak, in this pandemic. Very few people are getting it. So I'm not sure it's going to play much of a role. I mean, the main people for whom it's essential are people who are immunocompromised and can't respond to vaccines, right? So they have to be given antibodies. And in fact, in those, they may have selected for these variants like 501, who knows? But the other part here is that polyclonal sera is what most of us are going to make in response to immunization or infection, right? In the Nussenzweig paper, they say if they check polyclonal sera from these immunized people, they say they have reduced efficacy at neutralizing variants with E484K or N501Y or a combination of them, right? They say a small but significant margin, to which I would say, what does that mean for people? We have no idea if that means anything, right? Because these are in vitro neutralization assays. And just an hour ago now, a paper dropped in bioRxiv where a different group did the same experiment, neutralization of B117 lineage using pseudovirus, the same assay that they're using in the Nussenzweig paper, and they used sera from people immunized with the Pfizer vaccine. And they say equivalent neutralizing titers in all cases. So in their hands, there's no difference, whereas in Nussenzweig, I think it was a 1 to 3-fold difference in neutralizing titer. So, that's attributable to experimental differences in different labs, I think. I think the bottom line is 501Y, A484, 417N, I'm not worried in terms of vaccine responses about those. Maybe some other ones are going to pop up in the meantime, but those, I think the vaccine's going to work against them, right?
Oh yeah, no, I agree. And I think the game for the virus adaptation that we've seen so far, and for kind of in the next turn here, is the pool of natural infections. Like this is by far in naive hosts. This is right. And then now, and so then the question, which I think is a really interesting one, is what is the dynamics between the virus populations as they circulate both in naive hosts that have never seen or where you are naive to, you have never mounted an immune response to this flavor of a coronavirus, versus folks that have been vaccinated or have been naturally infected. So whether or not a reinfection sort of gains hold or has any clinical outcome, but viruses will show up. And so there's some interesting, you want to be very careful not to draw too close analogies, but there's some interesting from an evolutionary standpoint, thinking about how these populations of virus dynamics can kind of happen over courses of year or two, seasonal changes. And some of this comes from science buddy Scott Hensley, whose lab is at Penn, and he works on influenza. This is actually this is mostly work from his postdoc with Jonathan Udell, who we've heard on some of the podcasts on TWiEVO in particular recently. Really interesting, creative guy, great scientist. And so Scott was thinking about, or looking at, what happens with some of the antigenic drift, which is sort of the some of the main energy coming out of influenza epidemics on a seasonal basis. And what he found, looking at kind of some similar assays, which is looking at neutralizing antibodies to receptor binding domains, in this case, different proteins, obviously, that very commonly you would see very quickly that the virus increases affinity to the receptor. And that this might be, he proposed, this is an outcome to avoid some of these neutralization antibodies. Sort of the higher the affinity, the harder it is for the antibody to have access to the virus shape, the virus epitope. And but what he also noted is that actually those viruses do worse on naive individuals. And so you have this kind of back and forth as the virus is circulating between whether the virus is going to outcompete other viruses in the population based on the host and whether they already have an immune response or not. And so I think it's worth actually keeping an eye on that in this sort of coming year.
Yeah, because 501 is at the receptor binding site, right?
Exactly,
at one of the interaction sites, yeah. Now, Nels, that mechanism is interesting, but there are certainly antibodies that do not block attachment. They neutralize by other mechanisms, right? So they would not be overcome by an increase in affinity, right?
Agree completely. And that's one of the real challenges here of wading through this, is there's so many things happening at the same time in terms of the biology in terms of, and that's kind of the point actually. So that I think it's worth stepping back and kind of taking that slightly bigger picture of view, is not only in some ways in our training or how we think about whether it's the activity of the virus or the activity of the immune system or the interaction there, will sort of influence the way we look at the process in some cases. And so, for an epidemiologist, you might think, oh, the virus, we see more transmission. Maybe the secondary attack rates are higher, things like this. So the virus is transmitting. Structural biologists might see a difference in the binding interface, and that or a virologist might see something different in the ability of the virus to gain access to the cell or avoid the immune system in various different ways. And the truth is, evolution kind of doesn't care whether it's just who makes it, who over replicates, whether that's a neutral process, whether there's selection acting on it, and everything in between. And so we talked to, I'm trying to remember, Matt Hahn, I think, a great population geneticist, about this idea, the spandrels, the architectural feature in weather. So you look at this, so these highly decorated arches, right? And you look at it and you say, oh, wow, the architect must have put that there so that you could decorate these things. But evolution, that's not what, this is. So anyway, worth stepping back, I think, from this bigger evolutionary view as we try to untangle some of this and realize that actually we're talking about maybe different behaviors, both of humans and viruses, but that there's a sort of a bigger process going on here that doesn't have sort of our blind spots or biases in some cases. And so anyway, I'm not quite doing justice to Scott's influenza work, which I think is fun to kind of weigh maybe as a analogy or as maybe an echo of what might be going on in real time in SARS-2. But I have the link to, he did a little Twitter thread on this. And so we'll put that in the show notes. But anyway, so why don't we go back to the virus?
Hey, can I ask you a question, Nels?
Oh, of course.
So,
yeah.
One of the things you were very interested in last time was secondary attack rate, right? And you said at the time 3 weeks ago, we didn't have enough good controlled data to conclude anything about it, at least in the UK. I don't know. Are we going to come into that in our discussion subsequently today?
Absolutely. Let's get into it now. So and now we're back at the virus, right? So how are these populations evolving and what properties do they have? And so
by the way, Nels, just that Grinch site that you picked up last time, from a student of Eddie Holmes. She has now a nice map. When you go to the site, she has a map of the three variants: B117, B1351, which is the South African one, and BP1, which is the Brazilian one. And you can see where it's been circulating locally, where it's been imported, and where maybe it's not, right? So it's a very nice map to look at. I highly recommend it.
Agreed. Yeah, from Amy O'Toole. And she also, I was just visiting there because I've started to kind of look at it every several days just to watch this unfold a little bit. But, the caveats are still up there, which is in terms of the data that's coming out, there's really hard. So as people are traveling, and then as there's more sampling, that the potential biases that are in the data in terms of how is the sampling being done, the fact that there was all of this excitement generated or interest generated in B117, for example, and then some of the assays that are available, all of a sudden everyone moved to that. Versus sort of complete random sampling. And so that makes actually some of these, epidemiologic measures really hard to, and I think that's still the case for as the virus has moved out of the UK. Now, at the same time, there is better data from the UK experience, since that, for two reasons. One is they just do a lot of genomes, in that to their credit. And secondly, the frequency of that variant or that lineage and all of the variants within that lineage has continued to, the numbers are quite high. And so because of that, now I think that, we were talking about secondary attack rate estimates. And again, this is like someone who's infected, what's the chance of one of their contacts becoming infected? And there is some new data just because there's been so much more sampling, and it's rough. I haven't looked in the last day or two, but at least sort of from a week ago, so it's about 2 weeks on from where we're looking at. I would say the notion that there was a higher attack rate is holding up, not at the original kind of advertised level of 70%, but maybe closer to the lower bound, 30%. But again, with some big, I think, error bars around that, those kind of estimates. And so that kind of data, I think, is strengthening from the UK experience, but still not enough sampling and not enough cases, in some ways, thankfully, at least so far, here in the US and in other countries. And so there are some other attacks on this without that data. So Trevor Bedford in particular just recently put up something, and I've got the Twitter link from his thread here, where he was trying to control for looking at genomes of SARS-2 as they're coming on from the UK, from where there are obviously the most numbers, from the US, and I think from Denmark, where also sort of kind of an intermediate level, and then in the US where it's pretty low. And so first he was trying to correct for not getting, to try to do this to take it into account the frequency from a more sort of random, as close as you can get to sort of a random sample, and then fitting this to what is known as a logistic growth curve. And so when you do that for the UK, that logistic growth follows pretty closely as you see the frequency of the virus go from, let's see here. So back in early November from about 1%, 2%, 3%, up to now 70% plus as we look at, coming into 2021. Now, he can get kind of similar fits. It's not as from the data coming out of Denmark and some of the data coming out of the US, but it's really noisy. And what's really, I think, important to look at, and again, I've got the link to this thread. I think it's worth kind of going through. This just came out on the 18th of January, 2 days ago. Important to note the difference on the y-axis, which is the frequency. So in Denmark now, it's gone from 0% to about 4%, and again over that sort of same time frame. And so the trick here, though, is we are the difference is working at that sort of 70% versus the 4%, and sort of what happens next. And in the U.S., it's even lower, right? So it's now a little above 1%. And so, I think this is where, at least for me, sometimes I feel like my intuition can kind of be a little bit of, sort of a hindrance on how I think about what's happening here. So the CDC, I think, came out a few days ago and said what we're expecting is that by March, it could be that B117 is sort of the same way as it's now dominating in the UK, that this might be dominating in the US. When I look at these numbers sort of at that 1% frequency, or it's really hard, like our intuition sort of like lets us down, and the modeling is really hard at these low frequencies as well. And so,
I agree.
So it's really kind of, but here's here is sort of the trick with this is that if we're thinking about this in terms of virus evolution or virology, right? We want the evidence. We want to know what's going on here. We want to know the mechanism.
Of course.
And this will happen, but it's slow. And so it's almost this, this danger. And we saw this last year, getting lulled to sleep by these 1% frequencies where all of a sudden, boom, it just goes. And so it's really fascinating. I think that the work that goes there to try to make that prediction, what goes into those predictions, right?
Nels, so you remember last year, the D614 variant arose, and immediately the genomics and the epi people said it's more transmissible. And I just read a paper in Cell where Andrew Rambeau is a co-author, and they say, there's PCR data and genomics data which suggests higher shedding, but that doesn't mean there actually is more infectious virus. And they say that's consistent with the epi. But in the discussion, they say, we do not know if this virus is more transmissible or if it was just in the right place at the right time. They admit it. Okay, after all that noise last year, and I, my gut intuition, Nels, was I'm really interested in the evolution of virulence and transmission. And so far, in my view, in human viruses, very little evidence from human outbreaks of changes in transmission that can be mapped to a genomic level. Now, part of the problem is that we haven't had much genomics in previous outbreaks, and I agree.
Yeah,
so right. If you were going to say that these mutations are causing increased transmissibility, I want to know for the textbook if that's right or not, because it's important to me. I don't know if you're getting, for my big picture of how viruses evolve, right? So I don't think D614 was ever shown to be more transmissible. And I just have the same feeling for these viruses. Nels, can we look at it another way? Can we look at it more broadly in terms of fitness? Instead of saying these viruses are more transmissible, can't we just say, and I think the level of data allows us that they're more fit at a population level, and we don't know why, right? There can be many reasons why a virus would be more fit in a population, and that's why they predominate.
Absolutely. And this, and I think, and that gets at this, I think, how the discussion is unfolding in real time and just sort of the way that different scientists come at it. This is a challenge. So, when an epidemiologist thinks about transmission and sort of these really short-term things, whereas a virologist thinks about mechanism and what goes into that. And so I agree. So I think moving to this sort of idea of fitness again, that was what I was kind of maybe trying to get at with this idea of evolution doesn't really care. It's all of this complicated stuff is going to come together and something's going to come out from that. It's going to include both, all these contingencies, all the neutral stuff, all of the, and so the process is the process, but how we describe it is different, and that's important. I think that's an area where we all need to work a little bit and try to understand how these different almost scientific cultures come together, and the different I'd say there are strengths and weaknesses in each of our approaches, and so how do we elevate the conversation in some ways? And in fact, we're seeing something similar to what you're describing with last year's 614 perhaps unfolding in real time in California. So there have been these sort of breathless, newspaper reports and media reports in the last that we've got another variant, and this one's called L45R. Also in the spike, and so in this case, there is some kind of noisy epidemiologic evidence, circumstantial evidence that this has come up in frequency very quickly in California. And by the way, California is in the middle of a really bad part of the outbreak. Not B117, but probably version 1.0, and then potentially this other variant. But the data, so the epidemiologic data isn't there yet, or hasn't been collected or analyzed yet. And so, founder effect and other kind of neutral processes are very much at play here. It's sort of a different scenario where it's those combinations of 3 mutations that at kind of coming together independently at once. This is the first time we've seen this one. And so again, that's sort of a very weak circumstantial case. But I think, in the field, or in our, not the field, but in the sort of conversations in this fast moving pandemic, there's almost this variant fever that we get. We see a genetic variant in the virus, and we just sort of lose our perspective for a little while. And so a lot of those same epidemiologists who a few weeks ago were saying, hold on, this B117 we should be paying attention to, are saying, actually pump the brakes on L452R, this California one. The data's not there yet. But that's also important, I think. Some variants are more concern than others. And as the data builds for these, especially for the ones that are at low frequency, how do we weigh that as we're kind of in this non-intuitive space, but potentially going into these sort of exponential growth phases? Really challenging. So, and that comes up. So you located this great quick study on virological.org. So this is from, and we'll put the link to this one as well. This is on our menu for today. This is from Brandon Larson and Michael Waraby at Arizona. And so they were looking at some of the data, sort of similar to, kind of complementary to what Trevor Bedford has been doing, with the genomes, but doing a slightly different analysis here. So instead of trying to fit to the potential growth of the virus coming up in frequency, they used a method called TMRCA, or time to the most recent common ancestor. And so there's a bunch of different tools to try to do this, to basically look at the genetic diversity, whether it's a virus or a host, and looking at sort of sampling current diversity and then trying to work backwards based on the number of mutations to get to a common ancestor, where based on mutation rates and then that diversity, can you sort of retrace in time where the common ancestor of all of them, and when did that happen? Now, just as a caveat, TMRCAs, at least from my experience, you get these error bars that are massive, and there's a lot of assumptions in the kind of, and you can do the techniques differently. But the sort of interesting point that they make from their analysis is based on just this very thin sampling, but trying to put a time on when was B117 in the US, because we don't have this level of surveillance. Their estimates come back to, interestingly, early November, about the same time that this thing took off in the UK.
Yep.
And so why is it then? So, so one very simple prediction, if that is true, and again, a little grain of salt here for TMRCA estimates. But let's just assume for now that it's a good, that's true, that the virus B117, the lineage, was starting to circulate in the U.S. And they're looking, I think, in particular at California and in Florida, where there's a few more local cases, a little more surveillance, and so you can get slightly more power in the analysis you do. And so then the very kind of, question that they pose, rightly, is, okay, well, hold on. If that's the same timing of, roughly speaking, of when we think this emerged in the UK, why is it that this has spiked now to 70% in the UK, whereas it's still just sort of smoldering at low frequency here in the US. And so it's a fair question, right? And it shows that, again, it sort of illustrates
it's important,
this
right?
complexity.
It's important
it is.
because, as we said last time, you can't base everything on what's happening in the UK. The virus is elsewhere. Let's see what happens. And now we're seeing, and I think this is really important, that if you jump to conclusions based on the UK data, you're going to be misled, right? That's what I think.
So I hear what you're saying. I think, again, the question about that circumstantial case building across. So I think there is something to this idea that B117, that there's a selective evolutionary process or hints of adaptive evolution, but we don't know yet. And what happens? And so when the CDC or epidemiologists like Bedford predict that come back in March in the U.S., and that's when this thing is going to really take off.
I don't know how they can predict that. I don't know.
It's real. This is really this is the craftsmanship of epidemiology, and they might get it wrong, right? I mean, we've had all these twists and turns, and there's all this complexity there, and this is that sort of, that flat part of the curve before you go up, and the challenges there that come into this, but it's different. So, and it's not just the numbers, right? Because if it was, then L542R, which has come up in the Warabi and Larson say, well, maybe this guy, the reason that B117 hasn't come up yet in California is that it's competing with L452R. But here, then the epidemiologists at the same time are like, hold on, pump the brakes. That could be founder effect. And so and certainly there are founder effects, which can work in both directions, right? So if there are a few cases of B117 seeded, and let's just say by chance that got into an individual who has zero contacts, maybe they're infected with it, but they're asymptomatic, but they just they're hermits. Like and they had this one exposure. I mean, that's great for us if that, then all of a sudden the founder effect means that it's not going to go on despite, how this virus population or this lineage might be adapting. But my goodness, it is a complicated scenario.
Nels, one thing I don't get, and I don't think anyone has a handle on this, is actually if B117 is more transmissible, how much more is it? How much more transmissible would you need to be to predominate and to displace another strain, say? Because the number that they throw out, 50 to 70%, I think that's nonsense. That's based on genomic data, which is not reflective of an infectious virus at all. So what do you have a handle? Do you need 1% more? Is that going to do it? 10, 20? We have no idea, right?
So just by, you can do the calculation. So in a non-complicated real life situation, even a very small level of transmission, even 10%, that's a big deal.
Okay.
Because of just the notion of exponential growth. But there are all these other things weighing against that, right? So that's even something, so that's a big deal. But there's also a danger here. I mean, this is also, it feels to me at least, like a really complicated moment for scientific communication. Because if you go out with a really strong statement that this thing is 70% more transmissible, and then you come back in a few weeks and you say, oh, well, maybe it's 50 or 70, or maybe it's 30, or maybe it's even 10%.
I agree.
Like, to me, this is like flashing danger signals to the public, which is, first of all, you told me it was what sounded a lot worse a few weeks ago, so I'm going to let my guard down. And secondly, you lose that this sort of teaching moment potentially, which is 10% increase in transmission is massive if as that unfolds and under scenarios of exponential growth. And so, for me at least, I feel like lost in all of this conversation potentially is SARS version 1.0. And we talked about this, I think, a little bit last time, which is and actually you can look at this now in the UK. So if we just set aside B117 for a moment and just look at total cases. And so, a big response in the UK in the last month or so, almost, kind of going back to closer to something like a shutdown. And in fact, if you look at now, the cases it looks like they've peaked and are starting to come back down. Now, of course, we've done this sort of, waves of peaks and we're not out of the woods yet. But the take home for me is, changing human behaviors here can bend the curve. Sort of some of the very early public health messaging we had on flattening the curve. We live in this world right now. Of course. And so I think there's, so certainly we need to do the surveillance. We need to look at the evolution. But for me, again, it's sort of what's the context here? And as an evolutionary geneticist, how do I step back and think about this sort of in the bigger picture? And I'm still stuck, I guess, at the starting line in some sense, which is that spillover event where all of a sudden SARS-2 started infecting humans. It wasn't here more than a year ago, or, give or take, depending on how you look at the origin sort of, or the spillover sort of data. That was absolutely massive step in what we're up against even today. And then I think we are starting to see the hints of virus adaptation, especially kind of from the measures of conversion evolution. BE117, the 501 mutation, that combination of the 3, 484. There's increasing mechanistic evidence on things like interactions with monoclonal antibodies. This could spill over into virus sort of replicative behavior in populations, even if the selection isn't sort of specific to, there's could be sort of these pleiotropic effects, these dual effects that are happening. But those are pretty modest evolutionary events. And if we look at coronavirus, I think so. To me, it still feels like coronavirus evolution as usual. Unfortunately, it's in this strain that has is asymptomatic in a lot. It's very easy for this thing to spread in version 1.0, and then sort of our fatigue as in terms of keeping up some of the really difficult public health and even the easy public health interventions, which we haven't done well at. And so even if the virus wasn't evolving at all, we would have what looks like these outbreaks just based on differences in human behavior over time. And then we're overlaying this evolutionary dynamic. But I think that's a little bit out of balance so far as how much that has influenced this. But I agree with the epidemiologists in the sense that even a 10% transmission advantage, if that, depending on the founder effects working in both directions, and then how what that means for potentially overwhelming hospitals, health systems, as you sort of go through these patchworks of people who are not wearing masks and everything else. This, from a public health standpoint, even sort of small steps along here can have big short-term impacts.
I mean, all right, two things. First, you mentioned science communication. And, a month ago, people said I was failing at science communication for not telling people how serious this was. But I disagree fully, because what I'm trying to do is tell you that they may not be right. I'm just trying to tell you the alternative. And so I think that's science communication. What the press is doing now, they have all concluded that the more transmissible viruses in the U.S., that's ridiculous. It's totally ridiculous, especially since it's been here since November. And as Warby indicates, in some places it hasn't taken off like we would have predicted. So I was just giving the caveats, folks. So not nice of you to say I don't know how to science communicate. But secondly, Nels, it's back to fitness. When one virus outcompetes another, it doesn't mean it has an implication for human disease. It does not. It's just that one virus is outcompeting the other for whatever reason, and it may not be an actual person-to-person transmission increase. And, I think, in my view, the best metric for transmission is the R index, right? And they said it went up 0.2 to 0.3 in B117. That's 10% increase, because 2 to 3 is the R naught, right? It's not 70%. The 70%, as I said, is based on PCR, which I think is terribly noisy and not indicative of what's going on here. So I think this is a lot of nuance here. And as you say, it's different scientists not being able to communicate, right? You got epis, you got genomics people, and then you have basic virologists like me who want to know, if you're claiming this, you better tell me why this is happening, because otherwise I don't buy it. And that's where I'm coming from. So just one question for you, Nels. Can't one virus just outcompete the other and have minimal effect on what happens in people?
Oh, yeah, absolutely. I think sure that can happen. I guess, yeah, I mean, I would, again, try to step back a little bit from this. So I agree. I think the way that some of our science communication and actually, I should go on the record here a little bit. So I was kind of surprised by this. So certainly I think we're all doing our best to try to communicate things, and under complicated scenarios, both the timing of it and everything else. I think where I was surprised is just the how personal things got, and and very quickly, and you know, and communicating is hard, and you know, a little more grace just in terms of the idea that we're all trying our best here to understand something and step through it, and that we're going to make mistakes. And how is it that we can maybe try to continue to learn, to elevate, and to grow as scientists, to apply the scientific process, right? We're all responding in real time. And we could, if we play back the tape on everything we've said in the last year, as we've been grappling with this fast moving thing, there's plenty of things that now we're saying like very differently. And so I don't know, I just feel like, a little bit of turning down, and, hopefully actually just, I really am inspired today just by the transition that's happening in our country, and sort of trying to
maybe that'll set a
grapple with the last 4 years. And can we use this moment, not just as, citizens in the country, but also as scientists in the country, to kind of take that bigger view and say, there's like, it's worth it to, and we'll get to this in some of our science picks, to think, to listen to some of the expressions of how people are thinking about how we write the next chapter in the history of our country. And I think as scientists, we kind of owe that as well. So anyway,
can I just interject?
Of course.
So I try not to get personal. I really do. But I have to say, Nels, you are the epitome of never making it personal. In all the years we've been doing TWiEVO, I've said things that are wrong, but you never once said to me, Vincent, you're wrong. You've never said that. You have said, like, that's an interesting idea. Here's another possibility, right? That's the way to do it. Not to say you don't know what you're talking about. And you do it perfectly, Nels. And I hold you to everyone. I said, never have an argument with Nels. And I'm happy to discuss the variants here because it doesn't get personal. So thank you, Nels.
It's not necessarily, that my approach is okay. Sometimes it's more valuable than others. And there are times when coming out strongly, like, make a difference. Anyway, but I think the bigger point here, right, and the point you're making is, what's going to happen. And this is what we all want to know, is what's going to happen with some of these mutations or lineages. And we can go on to that great Grinch tool, right, and continue to look at this, and to kind of keep tuning in as we're looking at the data as it comes out. But I think, so again, bigger picture, I think, one of the good news items from that burst of cases in the UK is that, at least in the last couple of weeks, and I think mostly because of human behavioral interventions, whether it's B117 or version 1.0, the cases are coming back down. And I think, just what I'm seeing is some pretty big behavioral changes around the holidays and into the new year, where we really let in some fatigue, where we let things. And so returning to that public health stuff, and then really kind of hunkering in for the vaccine, feels to me, regardless of what the virus is doing, like, this is our best way forward. And we do better the more we're unified on that somehow. Now, here's my last kind of scientific attack on this, and on the points you're raising as well. And this, I think, illustrates again, sort of the challenges of how we're navigating SARS-2 and the diversity of viruses that we're seeing around us. And this gets into, how do we even talk about these things? How do we name them as it comes up? And so, again, from Andrew Rambeau and company, this is on Virological. We'll post, I guess it's a Twitter thread I have, and this is from maybe a week ago. Some of the genomic epidemiologists, genomic virologists, let's say, in some cases, are kind of throwing their hands up in the air, which is, how do we even talk about this? So, even right now we talk about B117, but there's also N501Y. I even saw some folks are now referring to that mutation as Nelly. So because the N is for asparagine, the position 501, and then the Y for tyrosine. But then to just simplify, it's hard. Like, what does N501 mean to anyone who's not a scientist? Let's just take the N and the Y and then call it Nelly. And so, these variants of concern, we're kind of all over the map here, is the point. And it's really, it's adding, I think, sand to the gears of trying to understand what's going on here. And so, So what is happening? So when we say B117, what are we actually talking about? It's actually not a single virus. It's a lineage that we talked about this on the last TWiEVO, and there's variants constantly getting spit out. And so the original sort of version of from that B117 was described for its 23 mutations compared to the reference strain out of Washington. And of course, that's slightly arbitrary as well. 17 of those mutations, which lead to are non-synonymous or lead to coding changes. There's some deletions in there. So those are sort of thought to be potentially the most consequential. Again, and we spoke about this, I think, at length, and this still stands, is what's going on with that ORF8 deletion that we see independently. I think that continues to sort of float in the air a little bit. But then it turns out, so if you want to characterize B117, you don't need to have all 17 of those mutations. You need to have 5 of them. So you need to have that one at 501, 484, 417, and then I don't know actually the 2 others off the top of my head. And so the new notion that is being proposed is we should really be talking about collections of mutations of consequence or constellations of mutations.
How do we know they're of consequence, though?
That's exactly. So that's exactly where I'm going with this. And I think this illustrates again why we do need to both communicate and cooperate across disciplines. Because I think as virologists, as evolutionary virologists, we would look at this and we would say, well, okay, how are you going to pick that constellation of mutations in the combination of them? Because we don't. So it's very easy to catalog these in one sense. We're still in the U.S. in particular, we're behind on doing this compared to the UK. But you can get genomes and you can hold up certain standards and get good data sets. But you don't know the mechanism. And so when you're saying, okay, it's this constellation, is that based on that's shown up independently 3 times? And that to me feels like a stronger definition right there. But could it be that there's a 4th mutation hiding there that's important for a constellation, or that's sort of independent? But then we just go into this morass. And so I thought to try to kind of tackle this a little bit of what's not to solve it, but to just sort of illustrate why this is such a challenge. So there was a great Twitter thread by Art Poon, and he's a professor of viral evolutionist at Western University up in London, Ontario, Canada, the birthplace of TWiEVO, by the way, when we were at ASB together. And and so Art, and we'll put the link up in the show notes, has a great illustration here of the difference, or 2 trees of 2 different virus populations, and sort of the challenge here. So it's of hepatitis C virus and of SARS-2. And so what he points out is that, everyone is grappling right now, the genomic epidemiologists, with the problem of consensus nomenclature for SARS-2. But it's a massive difference in sampling compared to how we name other viruses, other virus populations. And so he shows hepatitis C virus. And again, the nomenclature virus nomenclature is tough anyway, but I think coronaviruses are particularly sticky in this one, and more so because of the sampling we're doing. But so he shows this tree. It looks more like a phylogenetic bush, just the way it's drawn. So, thanks, Vincent, for putting this up. It was perfect. So here on the left, we have hepatitis C virus, and you can see, so there's no root. So it's just drawn. There's, most trees that we see working from left to right appear to be rooted. They don't need to be, but there's an outgroup. Here it's just that sort of gives you the orientation of the tree. Here it's just sort of a bush where the center of it is sort of arbitrarily drawn at the middle, and then you see the diversification. So the length of the branches here reflects how different, how many changes have happened from the middle, and then the relationship between the dots, or the virus isolates in particular, illustrates the relatedness between them based on how close together they are. And so, and these are roughly to scale. So it's, so it's, or the scale here illustrates how different this is. So if we look at, these are, if there's a little bar here that illustrates 10% of changes, or about 600 nucleotide differences between these different isolates of hepatitis C virus. So these are all hepatitis C. It's the same virus, but you can see, the different clades, or they're called genotypes, is how they've been named. how easy it is to identify those, because there's these clear demarcations between them. They've changed so much, so they've had time, so they've gone through all of the intermediate steps. But there's been time for selection to act, or for neutral evolutionary processes, where these are just very different genotypes, as they're called, of hepatitis C. Now, let's compare or contrast that to the right here of SARS-2. And so if we look at this bar now, instead of 600 nucleotides, it's a slightly shorter bar, but instead of 600 nucleotides, this is 3 nucleotides. So instead of a 10% change, it's a 0.01% change. And so what this pattern that you see is sometimes called a star phylogeny, meaning that there's no there isn't as much definition to the differences between these guys. There's all these intermediate lines, and so these are lineages: the 20A, the 19B, the 19A, and it's really hard to differentiate between them, because we just don't have, there hasn't been the time for genetic diversity to accrue here. And so, and part of the problem is actually sort of, even though we have undersampling in the US, but there's a lot of, still relative to any other kind of, certainly like at this time scale pandemics, we have just a crush of sampling going on in terms of the genomics. And so, so hepatitis C, Art says, is my teaching example of a consensus nomenclature based on sequence variation, and it benefits from that deep evolutionary history. Whereas for SARS-2, the compressed time scale and direct sampling means a lack of gaps to define categories. And so, in that sense, this actually looks very much like just standard coronavirus evolution, but we've just compressed the scale, and we've done so much sampling that we now have created this new problem. Yeah. And so, some of these variants really do matter, but it's in this sort of sea of things that don't, and there just isn't that definition to differentiate what we should worry about and what we shouldn't. And then I think we pour on top of that this sort of variant fever, and wanting to, as we're seeing outbreaks here and there, wanting to associate that with wanting to pin the blame on the virus differences. And we're just not in a productive space. We don't even know how to describe it properly, because we're so zoomed in on this process over a short amount of time that evolution, kind of the ideas of evolution, sort of fail us in some way to really make sense of it. It's all kind of happening in real time.
I think that's basically where we are. We have, even though we're not sampling a lot, we still have too much data that we never had before, and we don't know what to do with it. And so things like associations are happening of genotypes, or I should say 23 mutations with transmission that shouldn't probably be made. And I think we need to back off and learn our tools a little better. Yeah. So do you have a solution for this issue, Nels?
My solution is to build those circumstantial cases. So to take each situation. So like just say a situation is an outbreak. So California, for example, dealing with, so certainly California, you can immediately say that the current outbreak in California, I think it's 3 million cases running right now, which is a lot, is not because of B117. Just because we know with the sampling there, it's still at quite low frequency. So most of what's there is kind of version 1.0. With some hints of this, so I would still put this variant L452R, whatever, as part of version 1.0, as sort of, in a sense, innocent until proven guilty. Is that a founder effect? That's still the process of that first wave, and probably, I think, reflects a lot with what happened over the holidays in terms of, human behavior and things like that. And so I'm totally open-minded and flexible and I think virus evolution is happening. And I would not be surprised. So I guess my take home is I look to the history of coronaviruses, and in most cases, the common cold scenarios where we haven't beat the common cold. We also haven't had the impetus to really try to mount a massive vaccine, because the common cold symptoms are pretty mild compared to the deaths that we're dealing with SARS-2. It's a very different animal, but in some sense, the way the virus behaves in terms of adapting to our immune system, I would not be surprised if it falls on that same sort of tempo of every 3 years, 4 years, again, sort of trying to extrapolate from some of the early returns from some of the data we've been talking about in other studies, that we might be in a similar category. Now, of course, I could be wrong, right? There's some crazy mutations hiding out or some sampling, or certainly, with the amount of the growth of the virus populations very rapidly, even within the last month or two, the number of mutations that are getting a shot it's not an insignificant number. Virus evolution, we're working with what we know about viruses and sort of the themes and those are rules, but rules can be broken. And so I guess I'm not like ready to say conclusively anything could happen. I think for the UK and what happened in the last couple of months, that there is good evidence that or some evidence, circumstantial evidence, a growing case that there was some selection acting on B117. How that unfolds now, is it the same process here? Obviously, and if Warabi and Larson are correct that the timing is roughly the same, it's different in the U.S. so far, and so I don't know.
I would say let's blame people, not the virus.
Yeah, or some of both. Like I think there's plenty of blame to go around.
I found there's an article here in Live Science, and they call it "Worrisome California Coronavirus Variant is Tied to Large Outbreaks," and that's the problem here. It's an association, and in any other situation, for example, we'd say in this country they have higher vitamin D levels in their blood, and they have less severe COVID. And that's an association that needs to be proven. It's the same thing here. We have an exponential outbreak in the UK, and it's by this variant. That's an association, folks. So I think you have to prove it. And you may say that's a simplistic view, Vinny, but it's not. It's the same kind of science. And so this L452R has been around since March. And so give me a reason why now it is doing something different in California. You could say it just arrived, but, all of this should not be headline material. You should get vaccinated, wear a mask, stay distant, blah, blah, blah.
Yeah. And honestly, so, the data, it's a lot of the epidemiologists that are continuing to sound the alarm for B117. Yeah. And I think should be because of what has happened in the UK and in the circumstantial case that's building are saying very different things about L452R. And so, here there's one Christian Anderson who's been, I think, really sounding a megaphone on pay attention to B117. Went on record on Twitter in the last day or so about the quote unquote California variants, including this L452R. We don't have an idea if it's more transmissible. We need a lot more data. There was these press stories without data or, are not worth anything. And also he felt that he was misquoted on this. So he said, that we should watch this variant. But his full quote was actually that it's very unclear if it's more transmissible or whether it's founder effects. The virus mutates all the time. These variants increase in frequency due to biases in sequence, biases in sampling, nearby super spreader events, and founder effects. And it's unclear if this particular variant falls into that whole picture. So that's an example of waiting for more of the data to come in. I think in the case of B117, Christian and others are seeing some of that data. They're seeing that circumstantial case. And so their level of concern is much higher for that one currently than it is for any of these.
But again, in the U.S., does not seem to be taking over B117, right? For some reason.
Well, yeah, and so agree. So we're back on that sort of the low frequency dynamics versus that spike when it goes up, and trying to predict that. I think Bedford thinks that it's on the modeling matches, that it's on that growth rate scale. And I think he and the CDC came out that they think that, so it's not happening in the 2-week process here, but in the 2-month process that, but obviously time will tell. We'll see. And, for my money, I hope that it doesn't take over for some of the reasons we've described, and that in fact, something else happens that's more human behavior-based interventions, including that vaccine. I'm really hoping that starts to pick up pace. But the jury's out on whether in this transition we really get the numbers that we need to start to bend the curve in a new way.
All right.
All right. So stay tuned. So certainly, if we wanted to do that comparison between our last episode 3 weeks on, I think more circumstantial evidence from the UK, but still very thin on evidence outside of that. And so, stay tuned.
Want to do a couple of emailed Nels?
Yeah, let's do that. So Tom writes a question from OG listener and supporter of Microbe TV. Is DNDS higher in the region of the SARS-2 COVID genome that is targeted by the RT-PCR test? Is it possible to detect a genetic conflict in the test regions? If so, would it be possible to use this estimate for how well testing works at a population level? Based on listenings to TWiEVO, I think the stock answer would be the evidence of genomic conflict can only emerge more slowly. But now, with so many cases in such a large data set, maybe a larger signal-to-noise ratio would enable quicker detection. I think a measurable conflict would also suggest that the tests should not overuse the regions targeted by the vaccine. To anthropomorphize, the tests could train the virus to escape the vaccine. Perhaps this effect could be quantified with data or estimated in silico based on the mutation rate. Since different countries use different primers and at least 6 of the primer sequences are published, maybe there's enough data to begin to do statistics. And if the effect is masked by bias in the data set, it'd be interesting to quantify and track down the cause of the bias at the population level and find policy implications. This is from Tom, just a curious engineer. P.S. When I try to do this sort of thing in my field, I usually discover yet another inaccurate or expensive thermometer. And this was sent after our last episode of TWiEVO. So, yeah, Tom, some good questions here. And hopefully actually just the conversation even in this episode starts to get at that. And, and actually I think you hint at that, which is, so thinking about signatures of evolutionary conflict or of sort of recurrent mutations, non-synonymous mutations, starting to show up. Really difficult, I think, given some of those issues we were just describing with the oversampling at a compressed time point, like the kind of hepatitis C version versus the SARS-2 versus some of the other pandemics, HIV, for example, where we have, now in some cases 40, 50 years of data of tracking virus evolution over those times. And so, are we seeing evidence of what might look like an arms race? I think the answer is, or is this does this fit into the model of a genetic conflict? I think it does from that longer view, the same way that most viruses do and the way that other coronaviruses do. And so I think what we're just like glimpsing at sort of those first steps in a recurrent conflict. A lot of those metrics, the DNDS in particular, does well over longer evolutionary distances, although those algorithms have been tuned up from Art Poon and others in particular who have developed this for thinking about virus evolution. I'd say still early days there. And then the point about, the difference in how we're doing some of the RT-PCR based testing. I think this is a really important one to consider and to keep an eye on because, again, as we're sampling virus genomes and using tools as proxies. So the S dropout, like, if there's a deletion that shows up, which could be selected on, that would be invisible to DNDS, by the way, because it's not a point mutation. That can very quickly bias our view. So proxies are have great advantages in that they're quick ways to sort of genotype or to describe what's going on, but they also have blind spots, right? So you might get an S dropout, but it's a totally different lineage that has this massive super mutation that we haven't even seen yet. But we would put it in the bin of 117 just because that's what we saw. But the viruses are changing. And so, yeah, the way you test for them will influence your sampling. And depending on the assumptions you make for using those proxies could start to influence those data sets. And so, it's complicated. It's tough. And again, at this short range, we have this, I think this really very natural inclination here to want to get a handle on this, to want to solve this. But I think a lot of the tools that we've developed for more long-term, at least from an evolutionary standpoint, for thinking about that, sort of let us down for being in. And it's just, there's a lot of noise out there. And so getting to the signals is pretty difficult. And so again, the circumstantial case, I think, is starting to build in a real way for B117. But then as we are approaching new variants, they're going to pop up by definition every day. Again, we're sort of at the starting line in very sort of tricky space for knowing what's going on from a.
You can't have a more transmissible variant every week. It doesn't work.
Yeah.
Right.
Well, and there's virus competition, right? And then the whole and then sort of the notion of naive versus either post-infected or vaccinated hosts. And that dynamic is changing. And so, and how the viruses might compete differently, that transmit differently. Some of that, I think, echoing on some of the really interesting ideas from Scott Hensley's lab with influenza. And so, wow, there's a lot going on here. And
all these, the B117, they all have D614G, right? So how much increased transmission can we accommodate? It's just, you have to think about that. And I'm not sure everything is looked at independently, as you say, and you have to think of the whole picture. Anyway, Peter writes, he sends a link to a podcast with David Haig on the evolution of meaning from Darwin to Derrida. And he is a geneticist and evolutionary biologist who argues that it's perfectly sensible to perceive meaning as arising through the course of evolution, even if evolution itself is purposeless. Do you know this fella?
Yeah, David Haig is a very well-known leader in the field for thinking about some of the this idea of kinship theory. So actually, how does evolution read out on not just sort of, the very simple notion of you have a kid or there's offspring and survival of the fittest, but how do you then integrate the more complicated, just social situations and the impact of having grandparents, sort of it takes a village to raise a kid kind of thinking as applied to evolution. So very well known leader in the field on cooperation, competition, and other sort of core evolutionary questions.
So he's the podcast is Sean Carroll's Mindscape, and Sean Carroll, of course, is an evolutionary biologist. We did one of his papers once, I think, or talked about it. We've talked about him before, for sure.
We have. I'm trying to find out though. So there's actually.
Is there more than one Sean Carroll?
Yeah, this is a different Sean Carroll. So this is this is convergent evolution of Sean Carroll's here.
Oh.
So you're exactly right. There's Sean Carroll, who's was at Madison for many years, working on regulatory evolution to a large degree, and is now at the University of Maryland. There's another Sean Carroll who's a theoretical physicist at Caltech, and that's the fellow who runs this podcast.
Oh, okay. Because the Sean Carroll I know wrote the book All Things Most Beautiful or something like that. Yeah, okay.
Yeah, several. Sean Carroll, the evolutionary geneticist, is a great author and science communicator as well. And then there's Sean Carroll, the theoretical physicist who runs this podcast, and then brought in David Haig, actually very interesting. And I agree, this is worth checking out. So I'm glad that Peter brought this to our attention. Yep. Very
Let's
cool.
do two
Thanks,
more,
Peter.
Nels. Okay.
Yeah, sounds good. So Volker writes, referring to evolution to less virulence, sort of a controversial topic right now. Dear Nels, dear Vincent, thank you for taking the time to answer my letter on TWiEVO 61 regarding viruses trending to less virulence. I've listened to your answer twice. My understanding is now the following. There is the theory that over long evolutionary timeframes, viruses might trend to less virulence. There's unfortunately only one data point that we have, the introduction of myxoma virus to control rabbits in Australia. And here the reason for changing virulence might be more on the host side. Due to the long time frames needed, due to many factors involved, it won't be easy to test this theory. Is this correct? Then I think I should only be communicating by sciences in such a weak form as stated above. From the letters to TWiEVO, it can easily be seen that this theory causes confusion among laypersons as they try to predict what will happen with SARS-CoV-2, COVID-19 in upcoming months or years. I liked what Dixon said in the context in one of the recent TWiEVO episodes. By the way, I called it Kelsa virus because I mixed that up with a second rabbit virus control experiment from the 90s.
That's right.
Thanks again, and best regards, Volker. Yeah, so here we are again. So I do think that there might be some trend lines or some patterns as it goes. Like the longer the time, the more perhaps the sort of reductions in virulence. But and I guess maybe it gets a little bit philosophical here, but I guess we all really want answers to SARS-2, right? Is this how we've been at this for a year? Is this thing going to become more virulent? Is it going to become less virulent? Is it going to be the same? And some more practical considerations. When and if can we return to sort of life as we remember it, when we weren't wearing masks or social distancing, et cetera? And I think, as we've been discussing, I think some of those conversations are a little out of balance as we're, sort of moving from variant to variant at the moment and trying to grapple with this on this like massively compressed time scale. And so, I think at least for me as an evolutionary geneticist, I don't see an immediate answer, but I do find some comfort or some way forward in thinking about what do we know about other coronaviruses. And I think that to me, that's been a little bit missing from the conversation is the pandemic or epidemic strains from back in the 1950s, the OC43s out there, the common cold strains. How have they come through? And so we don't have the same, nowhere close to the level of data. There were some bad cold seasons that then sort of went through. And then we have the other corona, like maybe the other data points here, comparative points, are things like MERS or SARS-1, where obviously virulence was really high, but these things burnt out in different ways. There wasn't the same asymptomatic spread. Public health interventions worked really well, isolating in hospitals, and just the tempo and the sort of outcomes of those virus infections really worked into our favor, whereas this one hasn't so far. But to me, at least, I still am seeing some of those same, in the early returns of some of the papers we were talking about today, that the virus is probably, adapting on the tempo of a coronavirus, where, some of the data says that over kind of 3 to 4 year timeframes, you can imagine perhaps that our immune system will sort of will sort of let us down. And that, so I think one of the conclusions of the Nussensweg paper, or maybe the preprint, was that it does make sense to think about updating those RNA vaccines so that we are, re-upping, maybe, certainly not today or even, in the next year, but it could be that in 3 or 4 years, again, that's just an estimate that we're sort of back in the game there. As for the virulence itself, I think that's another in the Volker's question, obviously if this thing, it became more attenuated in the sense that, the death rate went down quite a bit, or the symptoms went down quite a bit, that could turn the curve as well. That to me also feel like if that does happen, and I think there's a couple of good reviews on this. I might, if I remember, I'll add this to the show notes, on the kind of leading theory on why those patterns of virulence reduction don't always hold, or why there are cases where we can imagine where virulence would go up depending on a lot of the dynamics, et cetera. And so, but yeah, for any one case, I think it's still really hard to nail down anything like to sort of, we're all doing some crystal ball gazing in a sense here.
Yeah, I mean, as a experimental virologist, I want data to support the hypothesis, and it's very hard in many cases to get that. But I think it's, as someone who has an overview and writes textbooks, that's what I want. Because I want to say in the textbook, is there any evidence for increased virulence? And, it's very hard to find it. So I say no. But when I do see it, then we'll put it in. And that's the same with transmission, right? This is a crucial point. All right, one more. From Mark, heard your request for Origin of Life books, episode 51, the books of Nick Lane, particularly Life Ascending, and even more so The Vital Question. The emphasis is on the role of energy in life's formation and evolution. As a layman, it appears to me that most biologists think the use of an ion gradient was some weird affectation life picked up rather than the property and a property as fundamental as DNA. Listen to episode 49 of Big Biology for an interview of Lane and discussion of the work. I'd like to get Lane on TWiEVO, actually.
Yeah, totally agree.
I love his books. I've read most of them, and Oxygen is another good one. Have you read any Nick Lane, Nels?
No, I'm behind on my reading.
That's all right.
As usual,
you have an active lab. It's okay.
I have been pointed to his work, and actually, I was really excited because we had him on the hook to come to a science conference that we ran a few years ago on kind of mixing together cell biology and evolutionary biology, with Nick coming in from that biochemist angle, right? Thinking about some of it. And he ended up having to bail on us at the last minute, unfortunately. But really impressive in terms of a great writer and also active scientist, sort of crossing between those. It's really hard. Really hard to do and really impressive. Okay, so I did. And so thanks for the reminder. So I did catch up. So I'm going to post a link, kind of just returning to Volker's question really quick on unifying it's a review from a few years ago. It's the senior author is Eddie Holmes, actually from 2004. So this is early days here, thinking about SARS-2 in particular, obviously, but unifying the epidemiological and evolutionary dynamics of pathogens, and starts to lay out some of at least the theory of some of thinking about or how to maybe frame some of these ideas in a more organized way than sort of my off-the-cuff answer here. I think worth looking at, and just let us know. It's I think it's old enough that it's not behind a paywall, and so it should be accessible. But so I've just posted that link next to Volker's letter, and so we'll put that in there.
Great,
fantastic. So,
all right,
science picks.
Yep.
I'll start with a couple, and this again, we're kind of hinting at this. So, this really hopeful day, I think, in the history of our country, the transition from the last administration to this one. And one of the things that caught me just in the last week was this announcement that the Presidential Council of Advisors on Science and Technology, the acronym is PCAST, is getting upgraded to a cabinet level position in the Biden administration. And so this is Eric Lander, Francis Arnold, Alondra Nelson, and Maria Zuber are four of the sort of top level scientists who've agreed to join this council. And so they had an announcement a few days ago. It's about 40 minutes, I think, but some really inspiration. I have a link to it. And I really was inspired, I have to say, by Alondra Nelson, by Francis Arnold, and Maria Zuber's, the stories they told, and some of the energy that they're bringing to the Biden administration in terms of science. And I'll just quickly read one quote that was part of Francis Arnold's response. So she's at Caltech. I think she's also a director at Alphabet, which is a company organized by Google. She also won the Nobel Prize in Chemistry in 2018, works on directed evolution of enzymes, and really sort of a science hero. And so she said, in part, that the agenda put forward by the president-elect and vice president-elect resonates with me not only as a scientist, but as a grandmother. When we put science back to work for the benefit of the people, revitalizing our economy, fueling our climate response, broadening our perspective as we rebuild around greater equity and opportunity, we are making a society that is worth passing on to our children and our grandchildren. It is an act of love. I really like that. I think she's onto it. Why do we do this? Why do we, as scientists, why are we in this game? And so, maybe kind of given all of the headwinds, a moment in our history where applying our science, speaking about our science, doing our science can really make a difference. And then I have two picks, just a last minute one with this morning's action. So, and this is blowing up all over right now. Really incredibly inspiring poem from Amanda Gorman. I think she's 22 years old, and recited her poem, The Hill We Climb, Wow. Just, I feel like wind in the sails here and great energy. She, almost some echoes are building a little bit off Lin-Manuel Miranda, the musical Hamilton. Some of that kind of cadence and energy in her poem that really kind of a call to what's ahead and some real optimism moving forward. So I've got a link to that as well as my pick of the week.
It's very nice.
How about Yeah. How about you, Vincent? You've got some inaugural related things to share.
So I missed the inauguration because I was outside being interviewed by Medscape. They came here and we did it outside for safety reasons. And I did see the Amanda Gorman reading, and I thought that was amazing. What a great reading that was. So I thought I would give you some quotes from previous inaugural addresses. Let's see if Nels can guess who these are.
Oh, great. I like this. Pop quiz.
So we have one quote: "With malice toward none and charity for all, with firmness in the right as God gives us to see the right, let us strive on to finish the work we are in, to bind up the nation's wounds, to care for him who shall have borne the battle, and for his widow and his orphan, to do all which may achieve and cherish a just and lasting peace among ourselves and with all nations."
That one sounds to me like Abraham Lincoln.
Yes.
That one's a little easier than some of the others, but yeah.
It was that was his second inauguration. Just the Civil War had just ended, and he's trying to repair the country, which had been torn apart.
Yeah. And was it something like 600,000 deaths in the Civil War?
Yeah. Huge. And then the next one. So, first of all, let me assert my firm belief that the only thing we have to fear is fear itself. Nameless, unreasoning, unjustified terror, which paralyzes needed efforts to convert retreat into advance. In every dark hour of our national life, a leadership of frankness and of vigor has met with that understanding and supported the people themselves, which is essential to victory. And I am convinced that you will again give that support to leadership in these critical days. You know who that might be?
Is this JFK?
No, that's FDR. No. His first inaugural. The Depression had been going on for 4 years.
That's right.
And he's saying we can do this.
I was somehow mixing up my initials. You've exposed my weakness in our American history.
I shouldn't put you on the spot. I'm sorry.
No, I like it. Yep.
And
it's
then
the ask not what you do for your country, ask what your country. That was what I was thinking of there.
Yeah, well, that's the next one, actually. And
okay.
Let the word go forth from this time and place to friend and foe alike that the torch has been passed to a new generation of Americans born in this century, tempered by war, disciplined by a hard and bitter peace, proud of our ancient heritage and unwilling to witness or permit the slow undoing of those human rights to which this nation has always been committed and to which we are committed today at home and around the world. And so, my fellow Americans, ask not what your country can do for you, ask what you can do for your country.
So that one I think is JFK.
That's JFK.
Yeah, that was, yep.
And I have one more for you. We must end this uncivil war.
I think that might be, is that Amanda Gorman from her poem that she just recited?
Wasn't that Joe Biden?
Oh, is that Joe Biden? Okay, yeah. Yep, that's right.
Which I think is exactly right. It's an uncivil war we're in. We're divided. We got to get out of this.
Good way to capture it, yeah.
I mean, very powerful words from some very good presidents. So there you go. Not a typical pick, but fun. All right. That's TWiEVO 64, microbe.tv, TWiEVO/TWiEVO. You'll find the show notes and letters. If you want to send a question or comment, TWiEVO@microbe.tv. And if you like what we do, please consider supporting us. We'd love your support. Microbe.tv/contribute. Nels Eldy, you can find at selvolution.org and on Twitter, Earlybird. Thanks, Nels.
Hey, thank you, Vincent. Good as always to talk some science and kick around some ideas. And hopefully some, new, fresh energy as we move through the inauguration, as we move into the months ahead.
You bet. I'm Vincent Racaniello. You can find me at virology.blog. Music on TWiEVO is by Trampled by Turtles. You've been listening to This Week in Evolution, podcast on the biology behind what makes us tick. Thanks for joining us. We'll be back next month. Until then, stay curious.